All right. So we have the moment generating function.
I found it.
Yes.
Just found the last episode of Dr. Who.
All right. Moment generating function. We have one way to calculate that it generates the moments is we take the derivative of e. We Taylor expand e to the tx. When we Taylor expand e to the tx, we get it. Another way is to interchange the derivative in the integral. And if we do that once, we get x e to the tx. What is the best value of t to put it at?
Why don't you have to take the derivative of fx?
What am I taking the derivative with respect to? No. I've integrated out x. This has no x dependence at the end of the day. It only has t dependence. So the x is a subscript that's a capital X. This is only a function of little t. So when we take the derivative, we get the following. What is the best choice of t to evaluate this function? 0. And if we evaluate it at 0, we get the integral from minus infinity to infinity of x fx of x dx. What does that equal? That's just the mean, or the expected value of x. If we were to take two derivatives, we take the derivative of this with respect to t again. Well, no t dependence, no t dependence, another x comes down. We get the integral from minus infinity to infinity of x squared e to the tx fx of x dx. And so now if I take t equal to 0, what do I get? Not the variance. I get the second moment. The variance I would have to subtract off the mean squared. So in general, if I take k derivatives, and the way you denote k derivatives is you put it in parentheses, and evaluate it at 0, that'll be the k-centered moment. So this is another way to see why we call this the moment generating function. You know, its derivatives give us the moments. Yes?
What would it mean to evaluate it at not 0?
You would end up getting some kind of combination of things. And so again, there's no t dependence here. So all that would happen is when you put in, say, t equals 1, you would now have the expansion of e to the x, and you would now have this kind of combination of the moments. So this is very different than the probability generating function. What was the key point to evaluate the probability generating function? Where did we want to study the probability generating function? 1. And again, the reason this is now 0 is the relationship between the two is a logarithmic change of variables. So the probability generating function at 1 is essentially the same as the moment generating function at 0. This just makes the algebra nicer. Alright, so let's do an example. Do you want to do the Poisson, or the Poisson?
The third.
The third, okay.
Poisson the third.
It sounds like, is that Shrek?
It could be. Poisson the third.
So the probability that x equals n is e to the minus lambda to the n over n factorial. So the first thing is, can we calculate the moment generating function? Probably, or I wouldn't have given you this as the only choice, right? So we want to calculate the expected value of e to the tx. Well, things are discrete, so we have a sum, n goes from 0 to infinity, e to the tn times e to the minus lambda to the n over n factorial. Okay? I haven't bothered preparing today's lecture. Why?
I like practicing your algebra.
I like practicing my algebra, right? We've done this so many times, you should be able to do it. Right? What's the first step in trying to understand this algebra? What should we do? Yeah, pull out the e to the negative lambda. So we'll have e to the tn, lambda to the n, divided by n factorial. The next step is a little trickier, but can you figure out what we should do next? how can I attack this algebra? If you could choose any value for t, what value for t would you take? 0. So if you didn't have t, you would have lambda to the n over n factorial. How would you evaluate that?
It's just
It's just e
e to the lambda.
to the lambda. So the question is, what does the factor e to the tn do? Is there any way to understand its role? Is there any way to combine things? We pulled out the e to the minus lambda. How should we handle the e to the tn lambda to the n? So when we didn't have that, we just had the exponential function. Is there any way to look at the numerator together and see an exponential function? What should we do?
It's lambda e to the t to the n.
Lambda e to the t. This is really the number e to the t to the nth power. If I put in parentheses like this, the problem becomes a lot clearer. So now, it's e to the minus lambda, sum n goes from 0 to infinity, e to the t times lambda to the n over n factorial. Alright, in the next line you'll see why I really like this. What do we get? This is just the exponential of e to the t lambda, right? And so I can simplify things, and I have e, I have a lambda, I have e to the t minus 1. We have an exponential of an exponential, okay? You may have seen something like this in a Calc 1 class, where your professor is just trying to give you a nasty function to differentiate. This time, it's actually important. This is actually an important function that we need to understand. The moment generating function of a Poisson is a double exponential. How do we calculate the mean of the Poisson? Take the derivative. So mx prime at 0, well let's do it slowly. Mx prime at t, I take the derivative, e to the t minus 1 lambda. Now I have to take the derivative of this piece. The derivative of this piece is just going to be e to the t times lambda. Right? And so now, when t equals 0, what do we get?
Lambda.
We get lambda. When t equals 0, we get 1 minus 1 is 0, e to the 0 is 1, times e to the 0 is still 1, times lambda is lambda. That wasn't so bad. What about the variance? What do we need to compute? Second derivative. And you'll see when I give up. Alright, so we have to take the derivative of this. What rule do we have to use? Product rule. So the first is the derivative of this piece. So e to the t minus 1 times lambda times the derivative of this, which is e to the t times lambda, times this piece, which is e to the t times lambda, plus this times the derivative of that piece, e to the t minus 1 times lambda, e to the t times lambda. Alright, so when t equals 0, what do we get?
Yeah, lambda squared plus lambda.
Lambda squared plus lambda, excellent. So the mean, so the variance is the expected value of x squared minus the expected value of x squared. So it's lambda squared plus lambda minus lambda squared, or lambda. There's the variance of the Poisson. So you have to ask yourself, was this a lot easier than the other approaches we had? This is not horrible in the greater scheme of things. Now, the more derivatives you want to take, the more involved it gets. Okay? What I want to do now is I want to show you a way to bypass taking derivatives. And the algebra we're going to see here will be very useful when we get to proving the central limit theorem. So look at this as either a way to bypass the derivatives or to put some useful algebra in the bank for later. So we have mx of t is e to the t minus 1 times lambda. And we know that this is 1 plus mu plus mu2, I'm sorry, mu2, mu t plus mu2 t squared over 2 factorial. You know, I know it's the moment generating function, so I know it's Taylor series. Its coefficients are the moments. Okay. Let's Taylor expand this. All right, well, when we Taylor expand this, of course, one way to do this is say, well, I know the Taylor expansion of e to the u, and let's plug in e to the t minus 1 lambda for the u. So we would get the sum, n goes from 0 to infinity, of e to the t minus 1 times lambda to the n over n factorial. Well, let's think about what we have. Which n is the easiest n to study? 0. Right, when I take n equals 0, I just get 1. Well, not surprisingly. Every moment generating function starts with 1. The 1 basically means you're a probability distribution. You integrate to 1, something happens. All right, nothing useful there. We want to look at the n equals 1, n equals 2. Well, let's look at e to the t minus 1. E to the t minus 1 is t plus t squared over 2 plus t cubed over 3 factorial. So when I look at e to the t minus 1, this is really t times something. Or it's t plus higher powers of t. So when I want to try to calculate what's going on, if I only care about the t squared terms, will n equals 3 contribute? What's going to be the smallest power of t when n equals 3? So when I look at n equals 3, I would get e to the t minus 1 cubed. I'll have at least a t cubed. When I look at n equals 4, I'll have at least a t to the 4th. The only things that contribute to t and t squared come from n equal 1 and n equal 2. So this is equal to 1 plus t squared over 2 plus yada 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 times lambda over 1 factorial plus t squared over 2 plus dot 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 squared lambda squared over 2 factorial. And then do I need to worry about anything else? Will anything else give me a t squared term? No. So now I just collect things. 1, I have t times lambda, so I have lambda t. My t squared terms, I have a t squared over 2 lambda. I have I have to square this. So when I square this, which gives me a t squared term? T times t. T times t squared over 2 is a t cubed term. T squared times t squared is a t to the 4th term. The only thing that contributes here at the order of t squared is t times t. Right? So we get a t squared lambda squared over 2, t squared lambda over 2. So we get lambda squared plus lambda over 2 factorial t squared. Plus dot 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 dot. Ah, the mean is lambda. The second moment is lambda squared plus lambda. There's your mean, there's your second moment. Okay? You have choices in this class as to which way would you prefer to do a calculation. Okay? There's lots of different ways. The question becomes, as you go deeper down the line, which is better? If you had to calculate the third moment, would you want to do this, or would you want to do this? And there's advantages and disadvantages to both. How many people here, I don't think there's any, but are physics people? Okay. What kind of differential equations do you look at? What order?
Second.
Yeah, for the most part in physics, you never really have anything beyond second order, which is really nice. Fortunately, in almost everything we do in probability, we don't need to go beyond second. We don't need to go beyond the second moment. We'll sometimes need facts such as the third moment is finite, or maybe I'm lazy and all the higher moments are finite. But we will not need, really, the third moment or the fourth moment, bless you. So because of that, fortunately, these are usually enough to get the level of results you need. We don't really need to go further. It's a great fact that in physics, second-order differential equations seem to be enough to rule the day. It's great that in probability, the first and the second moments seem to be enough. One of the, I think, midterm problems on the first midterm, which I think everybody has taken by now, if not, oh, please see me, was I give you a nice random variable and I want you to adjust it to have mean 0, and then I want you to adjust it to have variance 1. We'll talk a lot about this when we do chapter 20. This is called standardization. Some people call it normalization. Why don't I like the phrase normalization?
Because there's already a normal distribution.
Yeah, there's already a normal distribution. Now, of course, after normalization, with enough sums, it becomes normal. So there is some support for calling it normalization. But it's very easy to mix it up. You can standardize any random variable. And it's basically just saying, I want to adjust things so that my scale is mean 0, variance 1. If you do physics, potential energy, all that matters is change in potential energy. I might as well say 0 potential energy is on the desk, on the floor, on the ceiling. It's something where the absolute scale doesn't matter. Battery power is different. Battery power, the scale matters. The actual magnitude makes a difference. Potential energy, all I care about is changes in potential energy. I can set ground 0 anywhere I want. Whenever I have random variables, I might as well adjust them to have mean 0 and variance 1, so long as I have finite mean, so long as I have finite variance. If I have those, I can always make that adjustment. The great fact about the central limit theorem is that the higher moments that control the shape of the distribution don't really affect the limiting behavior of the sum. And if you sum n independent copies of the random variable, it's going to converge to a Gaussian. So the question is, well, it kind of seems a little bit silly that it should be completely independent of the shape of my distribution. Where does that matter? It matters in affecting the rate of convergence. How quickly do you become normally distributed? What is your error in being normally distributed when you have 30 sums? And that's where the third moment comes into play. And so when we do some of our calculations, if we take one term further, that would allow us to estimate how close we are to being normal. And it leads to a beautiful theory. We're probably not going to get into it too much in this course, but it's just nice to know where things go. Alright, should we do one more example? Alright, we just did a continuous example, so what should we do? Discrete. So do you want to do the binomial, the binomial, the binomial, or the binomial? I'll give you 4 choices this time.
Still the third one.
Still the third one. Interesting. So the binomial Pn, so the probability x equals n is, well, so x equals k, is n choose k.
So isn't Poisson discrete?
Oh well. Alright, we should have done the exponential then. Oh well, but
I mean, it was fun.
yeah, we'll do what. So we can either do another discrete or we can switch and do the exponential. You're the one who noticed. Do you have a preference?
This is too much power for you. Let's do the exponential.
Let's do the exponential. Okay. Moving on. So the probability fx of x is e to the minus x over lambda times 1 over lambda x greater than equal to 0. One of the advantages of being the professor is I get to choose the normalization. Right? I prefer this normalization. Other people who are wrong use e to the negative x times lambda. So either A, be very careful and check what book you're using, or B, only look at exponentials where lambda equals 1. Okay? Make sure you do this. This is not too bad here, but this really happens all the time. There are a lot of subjects that different people look at, and they have different conventions. You've got to get into the habit of checking what is the normalization and what is the convention. Alright, so the moment generating function is going to be the integral from 0 to infinity of e to the tx, e to the negative x over lambda times 1 over lambda dx. And this is just, of course, the expected value of e to the tx. What should we do? This is a good choice, so I'm glad you chose the exponential. What should we do? Combine them, right? For all the times I talk about how I'm against claiming Williams and against inclusion, this is one of the times where I'm all for it, right? It's the same as what we did before. When you have similar terms, combine them, right? We have two exponentials, don't have them separated. What is your concern when you see this? Do you have any concerns? Let's keep going. What are you afraid of? I'm sorry? Yes. What improbability? I'd almost like to do anger management, but I don't have the voice for that today. When you see this integral, what concerns you about this integral? Alright, take off your engineering hats for a moment. Alright, engineering hats are now off. Put on your mathematical hat. Now that you're wearing your mathematical hat, what concerns you about this integral?
Whether it's finite.
Well, that's finite, whether or not it exists. Okay. Now you can put your engineering hats back on and leave them on. Whenever I write down an integral, you should be very worried. Does this integral make sense? Can you give me a value of t where this integral makes sense?
0.
0. Can you give me another value of t where it makes sense? This is worth an M&M. Two M&Ms. Another value of t where this makes sense.
Anything negative?
Anything negative. Excellent. Because we don't know the value of lambda. So as long as t is negative, right, I only have exponentials with negative powers, I'm okay. Can you give me a positive value of t that will be okay?
1 over lambda.
1 over lambda. Right? Why 1 over lambda? Actually, wait, give me that back.
Yeah.
You have to correct yourself.
Yeah.
Why is 1 over lambda okay? So you would have e to the 1 over lambda x times e to the negative 1 over lambda x.
Then you get e to 0.
Yeah. Can you fix your 1 over lambda? You're close.
2 over 1?
Well, 2 over lambda is going to be even worse.
Anything that's less than
Anything less than 1 over lambda, you just missed. Anything below 1 over lambda, you're okay. That's my fault. I get off the M&M too quickly. But this is why for the... How many of you have heard of the Clay millennial problems? These are the 7 biggest open problems in mathematics. And each one is worth $1 million. Only one has been solved since they've been posed. Long story, the person actually declined the money. But in order to get the money, the proof has to stand up for 2 years. I don't think I can have a 2-year M&M policy, but I think I should do a little bit faster than that. So 1 over lambda just misses because then you get an exponential of 0. But as long as t is less than 1 over lambda, we're optimistic.
Wait, what's wrong with getting an exponential? I mean, aren't we just looking for a finite integral?
Well, but we're integrating from 0 to infinity. So I have no exponential decay. I need some exponential decay. So we're optimistic if t is less than 1 over lambda. And notice that includes all negative values of t. So when you're doing problems like this, your first step should always be build intuition before you do the calculation. Don't just hack away. What do I think should happen? I do not expect the moment generating function to exist for all values of t. This is very different than the Poisson. In the Poisson, you give me a value of t, great. I have a double exponential, I don't care. I can still evaluate it, it's a finite number. Here, the moment generating function will not exist for all t. Alright, so now we get 1 over lambda, integral from 0 to infinity, e to the negative 1 over lambda minus 1 minus t times x dx. Right?
Well, that would have been easier to see than it has to be.
Now when you write it like that, it's much easier to see what's going on. And you can see now that t has to be less than 1 over lambda. So the best way I know to evaluate this integral is to multiply by 1. Multiply by 1 over lambda minus t times 1 over lambda minus t. And the reason to do that is now I have e to the minus ax times a dx. So if I let u equal 1 over lambda minus t times x, then du is just 1 minus lambda minus t dx. And we will get 1 over lambda times 1 over lambda minus t, bring the lambda inside, and you'll get a 1 over 1 minus lambda t. And now you have the integral from 0 to infinity of e to the minus u du. What is the integral of e to the minus u du? What is this equal? It equals, you should be able to get it without doing the integration. Why is it 1?
Because it's the integral of the exponential density of parameter.
Yes, it's the integral of an exponential. What we've really done here is, this is an exponential with parameter 1 minus lambda minus t inverse. Because I like to have it down in the denominator. And so we just did some playing around to just get it to look into a nice form. This is just 1. So we get the moment generating function is 1 over 1 minus lambda t. So if you look at that, interestingly, the moment generating function makes sense for all values of t other than 1 over lambda. Do you buy it? If I put in t equals 2 over lambda, this makes sense, it's negative. So let's see. I integrate a non-negative function. Well, I only get the moments by taking derivatives and evaluating at t equals 0. So the fact that it's negative is not so bad. Yeah, for the moments. But the fact that I'm integrating non-negative numbers and getting a negative number, that's bad. Okay? So even though this makes sense for all t other than t equals 1 over lambda, we should be hopefully smart enough not to try to plug in, t equals 2 over lambda.
Haven't we already constrained our t though?
Depending on whether or not we formally constrained ourselves, yes. I wrote here just optimistic. So we should say, make sure. So we'll bump it up to, a commandment. Thou shalt not take t greater than or equal to 1 over lambda, or this integral has no chance of converging. Now, interestingly, at the end of the day, we get something that makes sense and agrees with the original function in the range where lambda is less than 1 over, where t is less than 1 over lambda. In complex analysis, this is called analytic continuation. This is very useful. So this is true if t is less than 1 over lambda. Alright, so how would I calculate the moments now? What would I do? So how would I calculate the moments of the exponential? I've got the moment generating function. I could take derivatives. That's one approach, is to take derivatives. There's another approach. What's the other approach? Yes?
Expand out into an infinite.
Expand out into an infinite series. It's a geometric series. Now, I wish I could sound louder and more excited. What does R equal? I wish I could say that louder. What's the ratio? I can say ratio. What is the ratio equal here? The ratio is what? So this looks like a geometric series. I'm sorry? Lambda t. So this would just be 1 plus lambda t plus lambda squared t squared plus dot, 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 dot. So what's the mean? So what would the mean equal?
Lambda.
Lambda. Now the second moment, it's a little bit harder. What is the second moment equal to?
No. 2 lambda squared.
Excellent. Why 2 lambda squared?
Because you need it to be divided by 2 factorial.
We really want divided by 2 factorial, so we have to put in a 2 over there. So now that we have that, the variance is 2 lambda squared minus the mean squared, which is lambda squared. And so we've now calculated the mean and the variance of the exponential. Again, you could easily take derivatives of this. This is not a bad function to differentiate. It's just 1 minus lambda t to the negative 1. Just differentiate using power rule. It's not so bad. Okay, hopefully this gives you enough of a justification for the name moment generating function. It generates the moments. And it generates the moments in several different ways. You can Taylor expand the exponential, you can interchange the derivative and the sum, you can take derivatives, you can take Taylor series expansions, lots of ways to do these calculations. Okay. Before we shift into chapter 20 and the proof of the central limit theorem, I need to collect some results about the moment generating function. And the idea is, if I have a trivial change of variables, I should be able to figure out how the moment generating function changes. So imagine I give you the density of a random variable x, and now I want to consider the density of the random variable 2x. Should it be hard to figure out the density of 2x if I know the density of x? The hardest part is to remember to put in that factor of 1/2 or the factor of 2 from the Jacobian of the change of variable formula. One way to make sure you put it in the right place is, well, once you have your new density, integrate it. Does it integrate to 1? If yes, you put it in the wrong place. You put it in the right place. If it doesn't, probably multiply by 4 or 1/4. Okay? So the question is, if y equals ax plus b, what is the moment generating function of y? Does it seem reasonable that we should be able to figure out the moment generating function of y in terms of the moment generating function of x? All we're doing is we're basically translating, we're adding b after we first rescaled by a. Sometimes instead of looking at ax plus b, people will put parentheses and look at a times the quantity x plus b. And in that case, we first shift and adjust the mean, and then we adjust the scale. So there's 2 different ways of doing it. We can either do it like this, or I could put parentheses. Well, if I can do this case, I can do the case with parentheses. That's just replacing b with a times b. So let's just do the slightly more general case. So the moment generating function of y is the expected value of e to the ty. I prefer to do these proofs very slowly, step by step, minimize my chance of making an error and forgetting something.
And this is assuming we know the moment generating function for x.
Yes. And so the answer is going to have to be a function of the moment generating function of x. And what else? A and b, right. It's possible that the answer might not depend on both a and b. Maybe somehow the answer only depends on a. Can you give me an example of something involving y and x where the answer depends on a and x but not on b? I'm sorry? Say it again? The variance. Right? If I just shift everything by b, I'm not going to change the variance. Right? So, it's possible the answer doesn't depend on a or b, but unlikely. Probably both will play a role. So this is just the expected value of e to the t ax plus b. Alright, so this is the expected value of e to the a tx e to the tb. What should I do now? What would be a good thing to do? Linearity of expectation, but I don't have any sums. But linearity is more than just sums. Linearity is sums and constant multiples. So what's the constant multiple here? So which one is constant?
TB.
E to the TB. So t is a fixed number, v is a fixed number. All I'm doing is I'm taking my expected value and I'm multiplying it by a fixed number. All right, well that's not a problem. That's just e to the TB okay. What does this look like?
Moment varying function of x.
Where?
T equals 18.
At AT. Put parentheses here. I'm evaluating the moment generating function of x, not at the point t, but at the point a times t. And so we get e to the tb, the moment generating function of x at at. And this is the moment generating function of ax plus b at t. It's probably giving it too much credit to call it a theorem. It's more like a lemma, but you know, I'm in a generous mood today. It's extremely useful. It allows us to see how things change when we standardize. Okay. Any questions on this formula from the moment generating function? So the idea is if we do trivial changes to our random variable, we understand how the moment generating function will change as well. Okay, so now it's time to move into chapter 20. Let's finally get to the point of the central limit theorem. We should have about 5 minutes left. Oh, 8 minutes left. We're a little bit ahead of schedule. Excellent. So chapter 20, central limit theorem. Okay, so the first thing is the concept of standardization. So let's imagine we have x1, xn, I, d, b, independent, identically distributed random variables. Say, with mean mu and variance sigma squared. Okay? So now, in this case, we could consider yn equals x1 plus xn. There's lots of things we could study. So the first most natural thing to do is to study the sum. Another thing people sometimes study might be xn bar would be x1 plus xn divided by n. I don't like either one of them. What's wrong with both of them? This is your chance to criticize freely. You know, what are the issues with these sums? So when you look at this sum, the mean is going to be n times mu, right? So the expected value of yn is n times mu. So the mean is growing. I want to be able to localize things. I don't want things to be growing. What's the variance of yn? I'm sorry?
N squared times
N, so, not n squared, n. The variance of a sum is the sum of the variances. I have n terms, so it's going to be n times the variance of each one, which is sigma squared. Alright, let's look at the other side. The expected value of xn bar, what's its expected value?
Mu.
Mu. And what's its variance? So I get 1 over n squared times the variance of each one. And I have n of them. So it's 1 over n squared, because I square the coefficient. I have n of them, and the variance of each piece is sigma squared. So my variance is sigma squared over n. The variance has n dependence. Are you happy with this?
Decreasing, isn't it?
It's decreasing. So what does this mean as n gets really, really large?
It's goes to zero.
So you're in the situation where you get more and more confident about the value. Is this bad?
Depends on context. You wanted
Okay, there's a lot of medical research where do people want to know, are they going to die tomorrow? For those of you who want the answer, let me know and I will tell you later. For most things, you like knowledge. Knowledge is good. In the words of Animal House, knowledge is...
That was good.
I'm sorry?
Is it just good?
Yes, knowledge
Yeah.
is good. I gave you guys a marshmallow for cultural reference. How many of you have seen Animal House? Knowledge is good. The motto of what college?
Isn't it just called college?
Nope.
It has an
I think it's Dartmouth was where they
Yeah,
filmed
it's
it.
based on
Faber College. Faber College. Knowledge is good. Okay? This is outstanding. This is what you want. Right? You get more and more confident. Your uncertainty gets smaller and smaller and smaller. Whose theorem could even be useful at this point? Yeah, even Chebyshev is fine here. The variance is getting so small. Right? This is essentially the weak law of large numbers. The only issue is that it's centered about the mean. That's not a huge deal. So often we study Zn, which is x1 plus xn minus n times the mean divided by n. And the advantage of that is it's going to go down to mean 0. But now the variance will actually be getting smaller and smaller and smaller. So sometimes we adjust things a little bit. So we might do square root of n times sigma. And so if we do square root of n times sigma, the expected value of Zn is going to be 0. And the variance of Zn, well, I now have 1 over square root of n sigma. I square that. I have 1 over n sigma squared. I have n terms. Each one has variance sigma squared. I now have variance 1. So the advantage of doing something like this is now I have a random variable that has mean 0 and variance 1. So things are going to not collapse all the way down to a point. I'm going to be at a scale where I can really study what's going on. So we will often use this standardization. And this is why in the central limit theorem, if we use this standardization, we will converge to a normal with mean 0, variance 1. Because we're now adjusting our things so that z has mean 0, variance 1. I want to end by risking talking about a log law. It's dangerous. But, I think we still have like a minute left. Yeah. So the change of base formula. Of all the log laws, this is the most forgotten. But for hundreds of years, this was in some sense the most important. So the log base b of x is the log base c of x divided by the log base c of b. And the power of this is, if you know the logarithms in base b, you know the logarithms, if you know the logarithms in base c, you know the logarithms in base b. You only need to know logarithms in one base. Centuries ago, people's jobs included calculating logarithms. They also included calculating values of trigonometric functions, calculating digits of pi. Mathematics has become a lot more exciting in my mind in terms of what you get to study. But people used to make log tables. The power of this is you only need one log table. If you know the change of variable formula, you can convert any logarithm to the base you know. That's essentially what we're doing with our standardization. So this is similar to standardization. Only need tables for a normal with mean 0 and variance 1. Kill the chart. Once we know the normal with mean 0, variance 1, we know the normal everywhere. Alright, so this is a good place to stop. Have fun with the rest of the exam. And then we will continue with chapter 20 on